Swayam Prabha. Digital India. Educated India.
Okay, so welcome back to a new class. Okay, so we kind of developed the Navi-Stokes equation in the last class, right? And developed the Navi-Stokes. We took the Navi-Stokes equation and developed it rather for to account for turbulence. Right, we did that in the last class, and the equation that we got was something like this. This is the final equation which we got, right? Okay, so this is the equation that we got last time, which we developed last time, and this is nothing but the time averaged Navi-Stokes equation, right? So the bars that we see here, this is essentially representing the time averaging. Okay, the primes here represent the fluctuating part of the velocity, and remember we wrote down the velocity as for example we will say that, for example, the x component of velocity, right, is equal to a time averaged part with a fluctuating part, right, and these are dependent on, when I write this, so this is actually, it depends on x, y, z, and t, and so on and so forth, even the other two components, right. So this is what this is the time average Navi-Stokes equation, right. Now, so again, so if you have this bar is representing a time. So gradient of a time averaged pressure, right, and this is del square of the time averaged of the velocity, and again velocity is essentially the generic three-dimensional three-component velocity, where each of these components, right, u, v, and w, are dependent on space and time, right. So we take a time average of the velocity along with a fluctuating part. So this is how we are representing turbulence. Okay. Now, what exactly? So that's that really. So what exactly is the deal here? Well, the deal is, now this term, if you look at this, this is the term. Right. Now, this is the term which is probably going to cause some computational challenges for us. Yeah. So we'll see what this means, and let us sort of talk about this equation a little more in detail and see what we actually are, what exactly are we dealing with here. Okay. So let me jot down a few points about these equations. Okay, so some salient points about this equation. Okay, so this term here that I've written here, this term. Okay, so that So let's just call that something. Let's just call it something. So this term I'm going to call as, say, A. Right? So what I'm talking about here is that term A. Right? So if I do that, it is never negligible in a turbulent shear flow. Actually, we'll get to that later. So obviously this is a fluctuating part, of the velocity. So if you look at this, so I represent the velocity in this fashion. Now I represent, so if this part is negligible, then the velocity is essentially a mean over a mean averaged velocity is the same as the total velocity, and there are no fluctuations, then we're not talking about turbulence, right? So if we are talking about turbulence, however, so then this term u dash cannot be negligible, right? And therefore, if I am considering turbulent flow, this term A in the Navi-Stokes equation is never negligible. Okay. Well, this is again not known analytically. So we have actually this is important because we actually do not have any idea of the value of this term, right, of the term A. We actually have no idea of what there's no way to know that. There's no analytical solution for something like this, right. So we have this mathematical expression, right, where we do have a velocity which we're breaking down into a mean and fluctuating part, but there's no way of knowing this a priori. There's no analytical expression for this, right. So that makes it complicated. So there's really no way of knowing, or as to the amount of fluctuation it could be, right. So is it going to be a large fluctuation? Is it going to be a small fluctuation? Is it going to fluctuate very heavily every second, or is the fluctuation going to be a little more gradual over time? We have absolutely no idea, right, when we're starting out. So now talking about this, now if I look at this now, right, now because of this time averaging, so essentially this equation that we have landed up here, this equation that I have landed up here, right, so it has actually thrown us several components which were not there earlier. So this is a term which we didn't have earlier on, right. We didn't. So this is a term which is coming in because of the time averaging, and we're using this for a turbulent flow, right. So we didn't have this previously. Okay. So if I may to sort of write that there, so time averaging has introduced new variables, right. And of course, if you see the number of components that you will have here, number of values of A that you will have here, for a typical, say I goes from 1 to 3 to J is 9, right. So essentially this is a tensor, okay. So what we are talking about here is, so just the time averaging has actually introduced, 9 new variables in that single equation, right. And this is in our quest to understand turbulence and to sort of quantify it, to measure it, and hence we're using the Navi-Stokes equation. So if we incorporate our definition of velocity for a turbulent flow, which is this, right? So this velocity term will actually have u bar plus u dash and v bar plus v dash and w bar plus w dash. If I incorporate that into this equation, right, I actually end up having tensor components of this new term that I've come up with, which is also when I'm just considering, just a single directional, unidirectional velocity. I'm not even considering v and w. This is only in the x direction. Okay. Okay. So a few things. So while we start out, a few things to write about this. Okay. Now, so these components actually. So this A term, okay, let's just say this A for the term A, right, this tensor components are related to the physical properties right, of the fluid, right, as well as the local flow conditions.
So it's important to note that the product of components of the fluctuating velocities is due to the nonlinearity of the convective term.
Okay. So essentially we are local flow conditions. So we are essentially talking about, say, velocity, geometry, surface, roughness, and also important, history. Okay, and there are really no physical laws, okay, to relate these. No physical laws exist to correlate the above. So what exactly am I talking about here? So we have this term here, right, and this is basically, so single component of velocities, it has 9 components, which is essentially it's a tensor component, okay, and it's a tensor component, okay. What we are understanding here is that, like we just said, that this is not known analytically. There is no way to figure out even a little bit as to the possible values, possible quantification of this term. Okay. Now this term has resulted because of the time averaging, right? And we're doing that only to assess turbulence. Now, however, what is known is that these tensor components, right, is related to the physical properties of the fluid. It is related to the physical properties of the fluid and to the local flow conditions. So things like velocity, even surface roughness, right, geometry over which this is moving, right, and also how the flow has been developing, and so in the sense the local conditions. So local conditions will be governed by what the flow has been doing just before we are looking at this space, right. So upstream history, right. So we're looking at what the flow was doing just before this location. So these components do depend on them. Are all dependent on these conditions. What is not known is what is the correlation. right? What exactly is the correlation? If given a velocity profile, given a certain geometry, can I assess these components? What is the relationship between, say, u dash and geometry, say the curvature or say the slope locally, right? Or for that matter, if the local velocity is if the local velocity is given, can I assess what u dash is, the fluctuating component is? So there really is no physical laws. There are no physical laws that exist to correlate the above, in the sense that if one had to try, if a mass of fluid is moving between, say, a point A to point B, right, it has to move in a certain way such that the basic physical laws, which is continuity, momentum, energy, are not violated. Those are the physical laws. But here there is really no physical laws to correlate the fluctuating components of the velocity, which is how we're defining turbulence, with the physical properties of the fluid or the flow conditions, okay, locally. And the local flow conditions also are affected by what is going on previously, okay. So, so this term A, so we're calling this, therefore, this is a kind of these are tensor components. So we can also call this essentially, this is also essentially an inertia tensor, right? It's an inertia tensor. So I am going to call this inertia tensor. Okay, so if I'm going to write this down. Okay, so right, so if I write, so I'm going to write it like that. Okay, I'm going to write this, write it like this. Okay. Now the point is, now if you look at this equation here, this term, right? So this term right here, the change in the pressure. This is the pressure force. This is the viscous force. What does this mean physically? Right? What does this mean physically? Well, nothing. Physically, it means nothing. I don't have any physical laws to govern that. And it does depend, this whole term depends on a few things, right? It is, physical properties, in the sense it is the fluctuating component of the velocity. But what does this term mean physically? Nothing, really. Okay. So this term, right, the inertia tensor actually, right, physically means nothing, right, really. So now let me therefore write it in this fashion. So I'm going to call this as, so again, like I said, this is an inertia tensor. Let us write it in this fashion. Let us rewrite this equation in this fashion. Okay, this is, so these are essentially the mean time averaged or mean Navi-Stokes equation. So let us write this equation as, so essentially this, I'm going to start from here. This, right? And let us just say I am going to write this as, right, I am going to write it this way, where this term, so I am going to write this term.
So please note that in some books, tau ij is defined as the Reynolds stress tensor, which is density times the average of product of the fluctuating quantities.
Right. This. So if you look at this, right, and so I'm going to introduce basically this expression, which is tau ij, so shear, okay. So and this, and I'm going to write it in this fashion, okay. If I do write it in this fashion, and then essentially I take the gradient of this, right. I take this and I should be getting back this equation. And you have to cross check whether that is correct or not, okay. This is an exercise I think I'd leave you to do. Why don't you try and do that, okay. Just cross check whether that is correct or not, okay. In the sense that take value, say, you know, I is equal to 1 and j is equal to 1, that will be one term, right, and they take the gradient of tau 1 1 and see what you get, okay. Okay. So once I get, so if I do that, so this is what I get here, okay. Now this term, so now here, now what is important here is, now this term here is interesting. Yes, this is clearly, this is laminar, and this is turbulent. So you see what the reason for writing it in this fashion, because when I look at this equation, right, this makes something to it is telling me the total acceleration of a fluid, right. The left hand side is nothing but total acceleration. So that is equal to, right, there is a certain time averaged change in pressure divided by the density, right, and then there is a viscous force which is happening, right, and I calculate that, right, and there is this term, right, which is the inertia tensor, as we said. It has components like in a tensor, and we're calling it inertia tensor, but this physically means nothing to me. So I'm trying to understand, I'm trying to give it some physical feel, physical meaning, so that it will kind of, you know, give me some understanding of what the fluctuating part, or what exactly a turbulent flow, you know, what does it physically bring into the equation, you know, what does it boil down to. I understand it looks a certain way, we've seen pictures of that, right, and there are a lot of fluctuations, but what do they sort of mean up to that, okay. All right, so therefore if I write it this way, so therefore then I what I do is I write it, I introduce this shear, right, tau ij, and then I say the shear consists of a laminar part and a turbulent part, okay. And what I'm saying is I'm leaving you to sort of work it out to see if tau, what I mean, how the gradient of this term should give us back this term that I'm looking at here. So I leave you to do that as an exercise to convince yourself that this is correct, and if it is not, then we should talk, okay. All right, so if when I write the shear in that fashion, so then this is the part which is laminar and this is the part which is turbulent, okay. Now again, I'm really trying to understand what this means. The inertia tensor, right. Yeah, I can see that, right. It is not stress as I see it, right. But if I write it in this fashion, so if I write it something in this fashion, then I see it does boil down to a laminar part and a turbulent part, right. It does have a laminar part and a turbulent part, right. Now that we have introduced this tau, right. So, if we have introduced tau into the term, so physically of course, it is not stress, right, but I have introduced this term tau, right, into the equation. So, mathematically right, mathematically this behaves as if that this total term, right, is a sum of. So, basically now it is saying that the inertia tensor, right, the inertia tensor is a sum of Newtonian viscous forces, viscous stresses rather, Newtonian viscous stresses. Newtonian why? Because stress is proportional to strain, right. What you see here is strain, right, del u del x is the strain, and then you multiply with the viscosity coefficient, right, and that is what is giving you the stress, right. You can figure out the dimensions of this, and I hope, and that should match that of a stress, which is Newton per meter square. Is that right? So, mathematically however, so the inertia tensor, the way if I look at this here is a sum of Newtonian viscous stresses plus turbulent stress. Turbulent stress, well again this tensor, fine. So, turbulent stress tensor, right. So, that is what I am seeing mathematically here, right. So, we started out saying that physically this means nothing, which is true, we are trying to understand this. So, what we do is we introduce the tau here, which is stress, and we understand that, we have a physical feel for it, right, that there is a certain stress, there is a certain strain associated with that is a strain. This is a viscous force that we are talking about. So, there is this differential movement between layers of the fluid. We are talking about turbulence, where is the layer? There is no layer here. At the same time, there is a certain viscosity element which is involved, right. So, there is the shear that we are talking about. So, we understand what tau is. Now, from in that context, right, then we have we want using this shear, right, we get these two terms here, and using the gradient of the shear is what we are supposed to get back this, right, and you should cross check that. So, when I write it in this fashion, then I see that this can be looked at as a laminar part and a turbulent part. So, while physically it actually means nothing, and it also does not mean any stress, any sort of stress, but mathematically, right, when I write this down, right, mathematically it actually behaves like it is a combination of Newtonian viscous stresses and turbulent stresses, right. So, typically therefore, right, in turbulent boundary layer, right, in a turbulent boundary layer, a term like this, UV time averaged, this thing actually is called a turbulent shear, right. This is just to sort of bring some association of what we are sort of writing out here. Okay. So, I think that should be, so that's all I think I have to speak as far as the Navi-Stokes equation is concerned. And when we introduce it, so essentially what I did is I introduced the velocity for a turbulent flow, which is writing the velocity in terms of a turbulent flow, which is a mean and a fluctuating part, and we ended up getting a term something like this because of the time averaging, right. Now, if I do get that term, what does this mean? Well, physically it means nothing. So, but we are trying to understand this. So, what we said is that we will introduce this term tau ij, which is actually like a shear, and when I introduce that term, I write it in this fashion. So, mathematically it so appears that the inertia tensor that we have here is a sum of Newtonian viscous stresses and turbulent stress, right. So, also in turbulent boundary layers, is known as, this term is actually termed as a turbulent shear, right. So, that is what that's all I have to say about about the Navi-Stokes equation when we use it for a turbulent flow. Okay. All right. Let's just okay. Now, moving on, right. So, moving on, I am going to write this down. So, energy equation for an incompressible flow with constant properties, basically first law of thermodynamics. Okay. So, we are looking at the energy equation for an incompressible flow, right. With constant properties. First law of thermodynamics. Yeah. So, what is that equation? So, right, you are familiar with this equation, or just sort of look it up. Okay. So, phi is the dissipation function. I will write this down in a bit. Okay. Now, when I say energy, when I wrote this, I said energy equation for an incompressible flow, right, with constant properties. What do I mean by that? Constant properties. So, what I mean by that is essentially that the CV, then the K, then these is actually a constant property, right. So, so there is a possibility when CV is not constant, right. So, when could that be? When could that be, right, when CV is not constant? So, if you are, so what we are not going to deal with here is very high temperature flows, right, where CV is not going to be constant. Also, in such high temperature flows, probably the continuum approach that we took to define physical properties of the fluid is not going to be valid anymore. Okay. So, I will not be able to define singular values of, say, the physical properties, density, temperature, etc., at such high temperatures. So, therefore, there is a cap on the amount of cap on the highest temperature that I can get to, right. So, we are dealing with that. So, we are dealing with a temperature range where we can still have constant values. So, like I said, with constant properties, right. Okay. Because so far we spoke about the continuum approach, where we were basically looking at space, right. Now, we are also looking at this where we are talking about the temperature, right. So, if you go beyond a certain temperature, then I think these are properties which therefore you say at constant temperature is not going to be valid. Okay. All right. Now, okay, so now let me write down the okay, the dissipation function. So phi is essentially is the dissipation function, okay, and phi is equal to del u del x square plus okay plus del v del x plus del u del y. Right, plus del w del y plus right plus del u del z plus del w del x squared. Okay. Okay. Plus lambda del u del x del v del y that that's quite a bit, right? Okay, so I think, but you can see what is going on here. Okay, you can see what is going on here. You have that. So we have all these constants that we're using here. So we have a dissipation function and the lambda. So this is equal to, right, from Stokes hypothesis. Right. So is that okay? So one more thing is a dissipation function, the phi is always positive, right? But lambda may be negative. Okay, lambda may be negative. Now again, what we will do is write this. We have to do this. So we will write this equation, right, as a time averaged function. Okay, so if I do that, so writing the energy equation, so I can say time averaged energy equation. Right, so that will be right is equal to okay. Okay, so again, where the time averaged dissipation function is equal to okay. This, right, Qi is equal to okay. So when I do that again, right, so if you look at this, right, so what you if you look at this term as laminar and this term is turbulent. So Q is nothing but flux, right. So so therefore, when I'm going to write it, so this, I've introduced that. So essentially, this is what it means. Okay. Now, for a boundary layer, okay. Now, for the boundary layer, the energy equation. Let's just see if this makes sense. The energy equation reduces to so if you look at this, I mean for the boundary layer, the energy equation reduces to. Now, what are the total number of terms here? So, what exactly are we, how is it, what is different for a boundary layer? I think it's kind of a little off question because we're specifically talking about turbulence here, but I just wanted to point out that essentially what is happening in a boundary layer is that the velocity which is in the direction of flow, which is u, right. So, the fluctuation of u, right, is not trivial in the y direction, in a direction which is perpendicular to the direction of its flow, right. And that is why we have the term del u, because I write this as, so I am sort of neglecting some terms, So, therefore, what I have here, so therefore, the change in the u component of velocity in a direction which is perpendicular to it, which is y, is not trivial. So, that slope remains, whether we kind of ignore others, right. And again, we also take the time average of the fluctuating part, which is u dash and v dash. Okay. And where has the third component disappeared? Well, it hasn't, because we are probably sort of saying that as we go in the z direction, the picture remains same, it's not changing. So, that's for us to, as a person who is conducting the analysis, it depends on what you are going to be able to consider. So, that is what we consider, that it is not changing in that direction, simply as that. Okay. So, therefore, the dominant velocity is essentially the u velocity, right, and its change in a direction which is perpendicular to it, which is y, is what is essentially being dominated here in the dissipation function. Okay. So, that is how it is different for if I am considering a boundary layer. Okay. So, as you can see that when I write these terms mathematically, right, it is just terms, it is just velocity, right. So, now it is for me to interpret as to when, if, how the velocity behaves, and that will decide whether the flow is at the boundary layer, or I am talking about turbulence, or I am talking about laminar flow. So, that is it. So, the computer code is just going to take the velocity and treat it as such. It is a velocity, it needs to multiply it with something, it needs to do this, it needs to calculate, that is what it will do. But it is for me to figure out whether that, the analysis of it should tell me whether this velocity is, essentially looking at a turbulent profile, or is it looking at a boundary layer profile. Okay. So, therefore, if I were to write this equation, so this is, I am going to term this as equation. So, this is again time averaged energy equation, right, and okay, I could sort of label this, and time averaged momentum equation is also something that we just did, and we have done time averaged continuity equation. Okay. So, now as you look at this equation, right, as you again look at this equation, I am going to just write this down, okay, after doing this. So, we have right now the time averaged equations of continuity, momentum and energy, right. Okay. So, they do give us some information, but not everything, and we still are at large thinking about more about the turbulent structure of the flow, right. For example, if I solve this equation, right, it is going to give me a velocity profile in a given domain over a given length of time, what is the heat exchange and things like that. Yes. But there are a lot of other questions which, when we were looking at how the disturbance is the disturbance, how the disturbance is distributed in a given domain, or distributed in time, how is the heat flow, what kind is the heat flow, right. If I have a large sort of disturbance going on, if I have a smaller set of, and we have talked about this, that disturbances are also are happening over different length scales, right. So, therefore, even if we solve these three basic equations, the governing equations, we still need more information to truly understand the turbulent flow. So, therefore, Prandtl, okay, Ludwig Prandtl, right, he suggested something called a mean mechanical energy equation. Okay. So, what he suggested is to form a mean mechanical energy equation, right. What is that? And what is this going to help us do? Well, we can discuss this, but let us first sort of write this down and understand what it means, and then automatically I think it will give us some sense of what this is all about. Okay. So, it is essentially a dot product of the, so this is essentially a dot product, right, of the momentum equation and velocity, right. So, dot product okay. So, this is this is a dot product of momentum equation and a velocity, right. And we take a time average, right. So, essentially it is a time average of the dot product of momentum and velocity, right. So, therefore, so we will sort of come to this, I think. So, I can write out this equation and then we will stop, and then we will come back to look at this equation and see what exactly are we talking about, and what each terms mean, because I think that is becoming a little bit of an issue. The moment we introduce the fluctuating parts of the velocity, we are getting terms, sure, but then we are kind of finding it a little difficult to make some physical sense out of it. Okay. So, I think Prandtl's analysis and this equation that we are trying to come up with is probably going to help us in that area. Okay. So, let us just say, so mean mechanical energy equation. So, it looks something like this. Right. So, the total rate of change of the mean mechanical energy okay. Okay, plus okay. Okay, and I take a time average of this. Okay, and we are going to stop here and take this up in the next class, and this is very interesting, Prandtl's suggestion, and we will see what this means. Okay. So, I think we will stop now and take this up in the next class. Okay. Thank you.